Earlier on in one of the videos, we saw the number of people with weird arms on their faces and the number of normal people changed over time. I'd like to give you another similar analogy. Imagine that there's a set of people waiting to go inside of Tesco's, sensibly socially distancing, but the shop hasn't opened yet. To begin with, we're going to start off with a high concentration of people outside of the shop. Inside of the shop, there'd be nobody. When the store first opens, lots of people will quickly be allowed into the shop. So the number of people outside will start to decrease and the number of people inside the shop will start to increase. The number of people outside of the shop will keep on going down until no more people are allowed into the shop at any one time. Similarly, the number of people inside the shop will keep on increasing until the maximum number of people allowed into the shop has been reached. At that point, for every person that goes out of the shop, one person is allowed in. That's when equilibrium is reached. If we were to draw a graph, instead of showing concentration in time, we had a graph showing rate in time, it would look just the same except for the fact that rate would eventually level off to be exactly the same. So if the blue line shows the rate that people are allowed into the shop, we start off very high, people are allowed in quickly, and it eventually levels off. For the people inside the shop, to begin with, there's nobody in the shop and people haven't finished doing their shopping so they can't leave. So people leaving the shop starts off at 0 and eventually people start leaving until the number of people leaving the shop is equal to the number of people going into the shop. So there's a 1 in, 1 out policy. The same thing happens if you've got two reactants, A and B, that can react reversibly. At the start of the reaction, A and B make C and D. There are no products at all at the start of the reaction, so the rate is high. Once there's some of C and D being made, C and D can start to react together to make A and B. But this is happening at a much slower rate than the A and B is being converted to C and D. The more of C and D that are made, the faster they can start being converted back into A and B, until eventually the rate that C and D is converted back to A and B is equal to the rate that A and B is being converted to C and D. That's like our 1 in, 1 out scenario, and that's when equilibrium is reached. You've now got a couple of questions to complete. Please pause the video and complete the 2 tasks before carrying on with the lesson.